Okay, hi everyone. So this is my lunch and meat talk for today, which is called Untangling the Blockchain. Now, I don't know why. In retrospect, I'm not sure why I chose blockchain as a topic. It just is just like an intriguing thing that's being talked about a lot at the moment. So I thought it'd be interesting to just actually kind of unpick what it is and see whether we can kind of take something out of it. This is going to touch on the technical aspects of blockchain, but it's not. I would say it's not a technical talk. The idea here is that everyone here now will hopefully leave this with hopefully an exact understanding of how cryptocurrency works and how blockchain serves to as the underpinnings of that technology. So with that said, rather than diving straight into the technicalities of what blockchain is, although blockchain is actually quite simple, it makes sense to actually build from the ground up by looking at what is a cryptocurrency. Because essentially, if you understand cryptocurrency and how cryptocurrency works, you understand blockchain by default, because the two are so intertwined that one can't exist without the other, really. So with that said, we're going to talk about cryptocurrency. So we're going to start really, really simple. So basically, imagine we have a group of 4 people. Imagine we have Mr. Butler. Imagine we have Steve. Imagine we have Jess, Carmen, and Ben. Now, imagine these guys they all go out a lot. They all spend a lot of money together, spend a lot of time together. And they decide, rather than always changing money around or remembering to carry cash or everything, they decide they'll just keep a ledger of who owes what, and then they'll settle up later. It's the sort of thing that lots of people do. So say Steve owes Carmen £10, Carmen owes Jess 15, Steve owes Ben 40, Ben owes Carmen 40. No, it's a pattern with Steve. So you get to the end of this. So you might keep a track of everything everyone owes at the end of this. But then this hopefully has already raised sort of some issues with doing something like this. Is that at the end of all of this, Jess has received £15. Ben is evens. Carmen's got £35 to her name, but Steve is negative 50. Steve can't afford to pay, basically, because of the way the ledger's set up. So unless he's stopped somehow, he's going to rack up loads of debt. So let's imagine this slightly differently. So imagine, rather than everyone just keeping a record of all the transactions, imagine our 4 people all decide to pay into a pot before they start going out. So imagine they each put £50 in at the start, and then we know that there's then £200 in the pot. So basically, as long as all the transactions that go back and forth between them don't exceed £200, and as long as no one ever spends more than what their current balance is in that ledger, then we know we're okay. So let's say, first of all, the pot pays Steve £50, and then Steve pays Carmen 10, so we know that Steve's got 40 now. Steve then owes Ben 40, so we know that his current balance is now 0. So if Steve then tried to pay Jess £20, he shouldn't be able to do that, because he's then taken more than what he currently had when the pot started. So basically, we want to prevent him from doing that. But as long as we do that, as long as we always keep track of the money in the pot and the money that anyone has in their account at any one time, then we can just run this ledger. This ledger can just run, money going back and forth, and essentially no money ever really needs to change hands, because as long as that pot is up to date and all those transactions are valid, then you can afford to pay. Now, hopefully, this all feels quite obvious. It's sort of not an uncommon thing that people might want to do. But if we were actually going to use a system like this to keep track of all our spending, then there are a couple of caveats that we'd have to consider. So, problem 1. So far, we've been assuming that each person is responsible for adding their own transactions to the ledger. So Steve decides to pay Carmen 10, Carmen decides to pay Jess 15, Steve decides to pay Ben 10 and Ben decides to pay Carmen 40. Now that's fine, but imagine that someone sneaky comes along and decides to say, oh, hang on a minute, Jess pays Steve £70 and then makes a swift getaway. We need a way of making sure that that can't happen, because otherwise he'll do it time and time again. Problem 2 is a question of maintenance. So we've got this ledger of all these transactions, but who's going to actually be the one that keeps it? Who's going to be the one that maintains it? Ben always wiggles in. We can't really trust any of these individuals, not because they're necessarily untrustworthy, but just because there's an inherent bias in you being responsible for a ledger of transactions of which you're a part, or being the sole responsibility. And if we decided to say, okay, well, we'll pass this off to like a central authority, like a bank or something, that works, but we have to find someone that we can trust and that is also going to act without bias. So this is where things start to get interesting, because actually the solutions to both of these two problems are basically at the heart of cryptocurrency and also at the heart of blockchain as a technology and its applications. So here we go. We're about to dive into the heart of Bitcoin. So we're going to be talking about, obviously, other cryptocurrencies are available, but we're going to be talking about Bitcoin because it's by far the highest profile. It's the one that is sort of synonymous with the tech. So that's what we're going to be doing. And I will point out, I'm not an expert on cryptocurrency as a whole, but I will point out a couple of areas of difference when they're relevant. Okay, so let's think about the first problem. So our first problem was, how do we make sure that we don't get people putting bogus transactions into our ledger? So when we see something like Jess pays Steve £70, we need to know that Jess is the one that has added that transaction. So if this were real life, one way we might do this with like a checkbook is for Jess to come along and actually sign her name in handwriting that is unmistakably her own, and then we can look at it and we can go, okay, well, that was Jess because the signature checks out. And by the same token, if Steve were to come along and try and fake Jess's signature, we'd look at it and go, well, that's a load of nonsense. So we'll say, no, we don't want that. And essentially, this is exactly what we're going to do. So the solution, as it sort of boils down to, really, is that we need a way of distinguishing a fake signature from the real signature, and it should be impossible, or at least incredibly implausible, for the signature to ever be faked by anyone. They should never be able to forge that signature. So that's exactly what we'll do. So we're going to take that real life principle of adding a signature, and we're going to do it, but in a digital way. And actually, we're going to go one better, because it's fairly plausible for someone to forge someone's signature in real life. You see that happening, but it's going to be nigh on impossible to forge the digital signature that we're going to come up with for signing our virtual transactions. So, solution 1. So we've got our transaction here, and what we need to do is we need to add some signature to the end, which I'm representing with a function symbol. We need to add some sort of signature to the end that unmistakably goes, yep, that was from Jess. Jess put that transaction in. So we think about the component parts of our transaction. We've got who sent the money, who's receiving the money, what the amount of money is, and then we need some sort of signature to come out of that. Now, we can't do an exact equivalent of a normal signature, i.e. it can't be a static thing, like your signature is the same every time you write it. If this digital signature were the same every time it was written, if Jess's digital signature was exactly the same every time, then it would only work once, because the second time Steve would just be able to go along and say, okay, well, I'll copy that, and then I'll just attach that to all the transactions. So we need to be a little bit more clever than that. It can't just be a fixed thing. So we're going to also need to add a unique identifier to each transaction. So let's say we have just a number, an ID at the start of our transaction. Otherwise, whatever signature we're going to come up with for this Jess pays Steve £70, whatever that was, even if it were unique to that transaction, it could then be copied to duplicate Jess pays Steve £70 over and over again. We need some way of making sure that every single time a thing is added to our ledger, it's completely unique. So that's what the purpose of the ID is for. So what we're going to do basically is take our identifier, person sending the money, person receiving the money, amount of money, and then we're going to combine it all together to with our, what we'll talk about in a second, how our signature works, to create something that looks like this, kind of monstrous long hash of characters, which is going to form our signature, and that's how we're going to validate that that transaction actually did come from Jess. So we can talk a little bit about how this works. So the way this is going to work is with a pretty common sort of cryptographic technique called private public key pairs. So the way this works is that you as a user will generate at the same time a pair of keys, one which is a private one, which is one that you keep to yourself. You don't tell anyone what that is, because if you do, then you're screwed. And then another one which is a public key, which anyone can know. Anyone and everyone can know that. And the purpose of both of them is, so when we have our transaction, Jess pays Steve £40 with the ID. The idea is that we use our private key, or it's often called secret key, so you don't have the two abbreviations both being PK. So we have secret key, and transaction forms our signature. And the purpose of the public key is to verify that that transaction was created using Jess's secret key. So, i.e., when you take your transaction, you've got your public key, which all of the other people in our group are allowed to see and know about. Check it with the signature that we've created. You can say, yep, that could only have been created using that secret key, which only Jess knows, so therefore that's a good transaction. Jess did that. And likewise, the inverse is true. If that doesn't check out, then you know that that's bogus. So that's pretty much how that kind of works, really. Let's think about our signature for a second. There's a couple of important properties about our signature. Now, this is created using a cryptographic hash function. Now, the idea behind the cryptographic hash function is that it's one way only. So they're very complicated pieces of maths, which basically in one direction will take some input and create something like that. But it's basically impossible. It's not technically actually impossible. It's just not really been figured out how to do it. To take that and reverse engineer it, even if you know that the cryptographic function that created it, you shouldn't be able to take that and reverse engineer it to see what went into it. Now, these functions, as you can imagine, the functions that actually produce these signatures are pretty important and are quite a hot topic of security and vulnerabilities and whatnot. What we're going to be talking about in the context of this talk is a function called SHA-256, which is, it doesn't really matter what it is or what it does, but basically cryptocurrency transactions are all secured with it. Your internet connection to most sites using HTTPS are all secured with it. So basically, if any vulnerabilities are discovered in it, which does happen with these functions, then we're all a bit screwed. So now let's return to problem 2, which is where we're going to store all these transactions. So we know that if we were to store them all in a single place, we'd struggle to trust that authority, because whoever owned the ledger could rewrite it and do whatever they wanted to it. So we could go to like a bank or something. This is pretty much what a bank does. But the whole point of cryptocurrency is to sidestep the requirement to have a bank in the first place. So that's sort of self-defeating. So we need something else, and we need something better, and we need something secure. So what about if we kept multiple copies of the ledger? So what if each person in our group actually stored a copy of the ledger, so that so that if our transactions get added to one but not to the others, everyone else can go, oh, hang on a minute, I don't see that on mine. Are you sure about that? But if transaction gets added to all of them, so Jess adds her own transaction which she's verified, the others can all go, yep, that checks out because it came from you, and then they can all add it to their copy of the ledger. And at that point, we go, okay, we've got multiple copies, this all checks out, and everyone's in sync with each other. But there is a problem here. So we've got 4 separate copies. Our problem is, how do we make sure that they all actually stay in sync? This is the sort of thing that looks good on paper, but how do you actually do it? Because there's going to be potentially hundreds, thousands, millions of these transactions flying around. How do we make sure that everyone is all working from the same sheet here? So, for example, to illustrate this problem, and the impact it could have, Steve could go, okay, well, I'm going to pay Jess £50, but he could broadcast that message just to Jess. You go, I'm not going to send this to the rest of the group. I'm just going to send this one to Jess. Jess will hear that. She'll go, yep, that checks out. Looks good to me because it's a valid transaction. Steve's got £50 to send, and he signed it. So, yep, that looks good. I'll add it to my copy of the ledger. But no one else has got that. Steve's found new ways to be sneaky, and he's just sent this to Jess. So, effectively, as far as the rest of the group is concerned, Steve still has that £50 to spend, and also, as far as the rest of the group is concerned, Jess does not have that £50 to spend. So it's easy to see how that's going to be problematic, or there's potential for fraud there, because Steve can then broadcast a message to someone else in the group saying, I'm going to pay you £50, and they can go, okay, well, you've got it, so I'll take it. And in that way, Steve can spend the same money over and over and over again. So we need a way around that. So this is where we're going to come into one of the most important topics in cryptocurrency, which is called proof of work. So, anyone heard of proof of work? The term proof of work? Ahmet probably has. Yeah. So that problem that we just described about keeping the messages in sync, by the way, is an old problem. It predates cryptocurrency. It's called the Byzantine general problem. I can send a link around to that. But that's the idea that if you've got people relaying messages around an army camp, how do you know that everyone in the camp has received the same message? The only thing you can do is to keep on going and checking, and then by the time you've gone and checked, you don't know what the state of everyone else is in. Proof of work is designed to solve that problem and stop Steve from being sneaky. So let's think about how it works. So think back to our signature that we had before. So remember how we said that one of the key features about this signature is that it's impossible to reverse engineer it. So it's impossible to take this and work backwards to establish what went into making that signature in the first place. That principle is going to exactly underpin how proof of work works and how we can now actually create something usable. So think back to one of our complete transactions with ID, sender, recipient, amount, and signature. So we know that if all of that is passed through a cryptographic function, we know that it's going to produce a hash. Now this is different to our signature. The signature is one of these as well. So don't kind of get confused. This is a new hash, but of the whole thing. And we know that that's going to be the same every single time. So every single time you pass that through this function, this SHA-256 function, it doesn't really matter what it's called, but I'll repeat it anyway, you're going to get this output. But imagine if, rather than just saying, yeah, we'll have that output, imagine if we actually put a sort of spec on this. We sort of said, actually, well, we want this transaction hash to result in a hash that starts with 6 zeros. Now we know it doesn't. It doesn't start with 6 zeros. So in order to actually produce a resulting hash that does start with 6 zeros, we know we can't work backwards. So we can't just put 6 zeros at the start and then try and reverse engineer our way to finding out how to do it. Basically, we're going to need something else. We're going to need an intermediate thing. So we're going to need some bit of data that we're going to include along with all of this that is going to then produce a hash which has 6 zeros on the end. And there's no other way to do this other than just trial and error. So we just start and we just keep on going until eventually we get lucky, and we find something eventually which gives us the hash we wanted, gives us our 6 zeros. Now it could take a very long time to find our sort of mystery input. This mystery input is actually called a nonce, which is always funny. So the purpose of the nonce is pretty crucial. The purpose of the nonce is to actually say, okay, well, I can now check that independently. I can go, okay, well, yeah, I know the ID, I know the sender, I know the recipient, I know the amount, I've got your signature, and if I add this nonce that you're saying, will meet these criteria to it, do I get a hash with 6 zeros at the start? If I do, then I can say, yep, actually, I know that you've done the work, because I know that the only way you could have arrived at that is to just try it over and over and over again. So you know at that point that the work has been done to create that transaction. And that is nonsense. I just wanted to get that into the presentation, really. Cool, so at this point it's worth taking one step out of our sort of theoretical journey and just making one little caveat to how Bitcoin actually works. We've been talking about this all in the context of single transactions. Bitcoin doesn't actually do that for optimization's sake. Bitcoin will actually group several of these transactions into batches to do this. Otherwise, it's already pretty crazy. It would be out of control if this process had to happen for every single individual transaction that wanted to go across the ledger. So the idea is that you take a batch of transactions, you find a nonce with and that's the proof of work, and then at the end of it you've got your hash, and then all of that, this process of taking a bunch of transactions and then performing that long, potentially very long trial and error process to find your nonce to get your hash, all of that is called Operation U-Tree. No, it's actually called mining. So when people talk about mining Bitcoin, this is what they're talking about. They're talking about trial and error, running a process of finding nonces until you find one, until you find one that gives you the desired output. And this resulting mush of transactions and hash and nonce is called a block. You see where we're going?
How can that not be sort of reverse engineering? Surely if that's proof, once you have the nonce, you should be able to work it back.
Yeah, I agree. You should be able to in theory, but in practice, it's never been done. Yeah, there's no physical reason it couldn't be done, because the workings of the SHA-256 function are known. It's just never been done. So yeah, it's complicated maths. I don't know, but it's just never been done. But it's not like literally impossible, like provably impossible to do. It's theoretically possible, but it's so difficult that no one's ever done it. So that's called a block. And by adding one more thing to the mix here, so we've got our block, if when we're creating another block, we also include in our thing the hash of the one that came before it to form our input, which then produces our next hash, then we're starting to chain them together. Yeah. And so this, block after block after block after block, is called a blockchain. And what this means is that because we know that a huge amount of computational work has gone into creating each block, because you had to find the nonce and all that stuff, our blockchain represents this huge sum of computational power that's gone into finding every single block. And that's really important. So we're actually we're gonna stop now and take a quick look. We're gonna try and do this and actually make our own blockchain. So this is not actually going to create any Bitcoin. We're not going to get rich or anything. This is all just a demo. And so the idea is that basically we're down here. We're going to specify how complex we want or need our resulting hash to be, and then when we start mining, you're going to see blocks start to appear. We're only going to generate 6 blocks, but you're going to see them start to appear, and you'll see basically the impact that this requirement has on how easy it is to generate new blocks. So if I were to set this at 1, 0, every hash just has to start with a single 0. This is going to happen almost instantly. Almost instantly, you're going to see 6 blocks appear. But let's do it. Yeah. So almost instantly, we've got 6 transactions, and you can see it's quite small, but this number here on each block is the nonce. So you can see that for all of them, it took almost nothing. The longest one was we had to try 22 different things to get to a 0. So that's no good, really. But if we were to set this to 6, like we said in our example, well, I hope you've got all afternoon. Because if I reset these, I'll be flabbergasted if we get a single 1. It would be really lucky. This, in all likelihood, will just run and run and run and run and run. But what we are going to do in a minute is we're going to do this with 4. Now, I'm kind of hoping that this will work, because I've had mixed results in testing with 4, but we're going to try it with 4. And hopefully this will give a good idea of the fact that an amount of effort goes into creating each block such that our resulting chain has meaning. I'm reluctant to say value, although that's what lots of people would say is value, but it has meaning. So this, in testing, it's taken roughly 40 to 60,000 tries to find one, but it's completely luck of the draw. So we'll stand here for a second and see if we can get a new block. Yeah. Basically, this is what happens. So this is what will happen with hundreds and hundreds of machines all wired together in farms running this sort of thing to try and find nonces. I think we're...
So does Bitcoin always use the SHA-256 encryption?
Yeah.
Never use the 128 or...
No, Bitcoin's always used this one. We're not playing ball here today, so I'm going to set it to 3 because I want to get another chain of 6 again, but with some sort of meaning to it. So if I reduce our complexity, so with an actual Bitcoin, so this complexity might be anything up to 30 zeros, something like that, requirement. We're talking serious, serious restrictions on the power. But once we've got our 6 here, we'll see another pretty important thing about the fact that we've got our blockchain is that as well as this resulting chain having at every step proof that work has gone in, time and work has gone into making it, because each block also contains the hash of the previous block, it's sort of immune to tamperability. If we were to move any of these blocks around, then everything that comes after it is now invalid. So if you were to take one of these blocks out or rearrange them or change the data that was in one of them, so we were to change the amount to something else, we can't do that in this demo, but we can just rearrange them, then it invalidates the whole rest of the chain. So in that way, it's fraud-proof by design. Which is pretty cool. So if I can go back to our presentation. So now we're going to take all of this and do I guess this is sort of the big reveal moment of the presentation. In my head it was going to be the big reveal moment of the presentation, but with everything that we've gone through to get here, it won't actually be that much of a surprise. But there is no such thing as Bitcoin. It took me a little while to get my head around the idea of this, in that we all know that obviously you can't like go and take Bitcoin out of the ATM and carry it around with you, apart from those little ones they 3D print, apart from those little ones that Dan carves for presentations on the news. There's no such thing as a Bitcoin, but I certainly assumed, and I think it's pretty reasonable to assume, that because it's like a digital currency, that there would be a digital equivalent, so that like a Bitcoin would be a thing that had its own identifier and all this sort of stuff, and there would be some sort of digitally traceable presence to it. Well, there's not. It's just not a thing. Basically, remember how we talked about at the beginning about this buy-in that would happen? There's no such thing as the buy-in. Basically, with Bitcoin, this ledger of transactions is the currency. So this, I paid Jess £30. That fact that number is now in Jess's wallet is the currency. There's nothing tangible backing that. Just this ledger of transactions is the entire thing. And the proof of work that's gone into it, I guess, is the value, if you like. But
So how do you know how many Bitcoins you've got?
because you have a wallet. So when Steve is paying Jess, what we're actually talking about is wallet with ID X is paying wallet with ID Y
How do you know what's in it?
money.
If it's not a thing.
Yeah. So basically, every time, this is one of the nuts things about Bitcoin. Point one. So every time a transaction is put out there, one of the processes is all these nodes that receive it would have to go, okay, well, Steve wants to pay Jess £50, let's say, 50 Bitcoin. The first thing that has to happen is we have to go, well, does he have it? Does this wallet actually have 50 Bitcoin to spend? And so one of the things that basically happens, first of all, is each transaction that goes up is verified against the entire history of the ledger until the origin of that wallet. So you can imagine already that that's a time-consuming process, but it happens. And if it's a question of where did anything come from to begin with, like where did Bitcoin even start from? So that's kind of what we're going to talk about now. So each time a block is mined, what happens is, and when I say what happens is, and each time, there's nothing like inevitable or scientific or technical about this. It's just a thing people decided. It's just how it works. Some amount of Bitcoin is added to the global pot. So in our initial ledger, there was a buy-in. Everyone put £50 in to start, and we had £200 in our pot. That doesn't exist in the world of Bitcoin. There is a pot, but the way that pot has been populated is through mining, and it's completely arbitrary. So basically, the first few times blocks were mined, basically what happens is the miner, this guy, he gets loads of lovely Bitcoin because he's done the mining. This is sort of the incentive for people to actually set up nodes doing mining, is that you'll get some Bitcoin out at the end of it. And you can do you complete histories of the complete Bitcoin ledgers of every transaction that's ever happened, every block that's ever been mined are available on the internet. And if you look at the early ones, like the first few, there's no transactions in them. Just a block has been mined, and then a Bitcoin reward has been there, and it's added to the pot. And every few years, the amount of Bitcoin you get rewarded for mining a block goes down. Again, completely arbitrary. There's no technical reason that has to happen. It's just what the people who have established Bitcoin have decided happens. So basically, there's a lifetime cap of about 21 million Bitcoin. There will only ever be about 21 million Bitcoin in circulation. At the moment, there's about 17.5 million. And I'm not sure when that cap's expected to be reached. But basically, this change, this halving of the amount of money you receive per block happens every 4 years. And the complexity that we talked about, i.e. 6 hashes, 6 zeros, 30 zeros, whatever, that's not a fixed thing. That's dynamically adjusted such that the amount of time it takes to mine a single block, hoping this is still making sense at this point because we're starting to just use the terminology, is about 10 minutes. So every 10 minutes, a block of Bitcoin is mined. Again, all of this is completely arbitrary. This is just things that people have decided to do, and this is just something that works.
How many transactions are in a block?
It varies. It varies. I don't know if there's a maximum. I don't know what the maximum is. But in terms of talking about, I suppose we can talk about this first. So in terms of so in terms of say you were to do a transaction, Kristen pays Dave 30 Bitcoin. It doesn't happen straight away. That transaction doesn't happen straight away. So basically, you put your transaction out there, it gets verified, as in like, is this a valid transaction, yes or no? So the whole network establishes that. At that point, your transaction is available to be mined into a block. And so this is the second way miners of Bitcoin make money. And this is one of the things about Bitcoin that sort of, when I heard it, was like, what? Why is anyone pouring money into this? Basically, the other way they make money is through a transaction fee. So if you want to pay Dave 30 Bitcoin, you can say, okay, well, in order to hurry this along a little bit, I'm also going to include a 0.1 Bitcoin fee for the miner. And you don't have to do this. This is optional, but miners are obviously going to prioritize transactions that include a fee, so because that's how they make money. So your transaction to reach Dave may take anywhere from 10 minutes to days, depending on the fee. And the average fee per transaction currently, or as of a year ago, I think, is $23. So every time you want to send someone any money at all, on average, you're also going to be spending $23, which sort of blew my mind. And again, it's probably one of the reasons that Bitcoin is, apart from the faddy nature of it, mostly popular for people that are like ordering like contract killings and stuff, where they sort of don't really care about the money as much as they want the thing to happen because they can't really shop around,
How does the miner get the transaction? How do they find out? I don't know, Kristen paid Dave.
So this is all broadcast. So every person is a part of this network of nodes on the thing just by connecting to do the transaction in the first place. So that's just broadcast peer-to-peer style, like Napster or whatever used to work. Peer-to-peer style broadcast to every node on the network. Not all of those nodes will be miners. Most of them aren't. Most of them are just people that are participating globally by keeping records of the ledger. But basically, that happens. It's verified by everyone, and at that point, the miners on the network will be working from this pool of transactions.
And multiple miners.
Yeah, and that's exactly how it works. So basically, it's like, this is why it's kind of like a lottery. So these transactions go out, and then all these independent people, or it's not people anymore. It's like data centers in China that have got thousands of machines all wired up. Unfortunately, it's not Ahmet in his bedroom anymore. All these people are competing basically, and it's luck. I mean, the amount of processing power you're putting behind it obviously makes a difference, which is why lots of people have been sort of priced out. But basically, they're all competing to be the one that mines it, because the one that mines it gets the reward. And at that point, the block goes out to the network, and then everyone updates. And the miners that weren't lucky were like, well, shit, better luck next time. I'll start on the next one, kind of thing. But what's good about this, and the way and why proof of work is important in the context of making sure everyone is still working from the same page at all times, is that because each block takes time and effort and resource to mine, that in a situation where you might have two competing, because this does happen, so you might have one person putting out this block, one person putting out that block, and saying that the previous one was, they might have the same previous one, and they might in themselves both be valid. But in situations where you have these competing forks, ultimately, that you can always trust whichever one ends up being longer, because the one that's longer is the one that's had more resource put into it. And the reason that works is that it makes it impossible to scam the system, over a long timeline, actually we can just demonstrate. I've got a slide to just demonstrate this again with. I just wanted to get as many examples of Steve being sneaky as I could into the thing. So thinking back to before when Steve is like, okay, I'm going to put out this dodgy block with this transaction in. Jess might believe it at first and add it, but ultimately she's going to start to receive blocks from other people that don't have that transaction in, and she'll know eventually that it's bogus, unless Steve were to control over 50% of all the computational power that's going into mining Bitcoin. That's the only way long term, in principle, you could scam the system. And that's a real thing, and that's a big thing. That's called a 51% attack. It's a real concern. It's never happened to Bitcoin, but it has happened to other cryptocurrencies. It's happened to Bitcoin Gold, which is a fork of Bitcoin. And it has happened to Ethereum Classic. I'm going to sort of stop a little side note to talk about Ethereum Classic, which is another good example of how nuts cryptocurrency is, and why, in my opinion, you shouldn't invest in it because it's mental. So Ethereum is probably the most well-known cryptocurrency after Bitcoin. Now, I can't remember. Sorry, what time? Oh, we're all right. I can't remember exactly when it was, but basically, like a year or two ago, I think, a venture capital group called DAO invested a lot of money in Ethereum, and then they were victim to a fraudulent attack on, let's just say their wallet got hacked into, essentially, simplify it to that. Their wallet got hacked into, and roughly $50 million worth of Ethereum was stolen and moved into wallets that it shouldn't be. And so the Ethereum people, the Council of Big Beardy Ethereum people, got together and said, well, what should we do about this? And there was a vote. And the vote, the choice that won out was to reverse those transactions, to say, okay, well, this was fraud, we're actually going to reset everything to how it was before. So they basically modified the chain to restore those funds to the wallets that they come from. But some of the beardy Ethereum people said, well, no, this violates one of the core principles of our thing, which is this ledger should always be immutable, and that should be set in stone, and it basically is tough shit that you lost your money. Don't write your password down on a sticky note next time, kind of thing. And so at that point, these people said, well, we're going to do this, and we're going to create a fork of Ethereum. We're going to call it Ethereum Classic. And at that point in time, everyone who has Ethereum also has Ethereum Classic. So if Ollie had 500 Ethereum, he's now got 500 Ethereum and 500 Ethereum Classic. So a lot of people made a lot of money by chance of this. They have different exchange rates and everything, but what the fuck? And we can talk a little bit briefly about investment, because it's one of the key things that one of the key topics around Bitcoin is how it's made people gazillionaires overnight, or it's made Armet nothing, but he's got a lot of money in a wallet that he can't get into. But we can, this volatility when spelled out in numbers is pretty crazy. So in January 2017, one Bitcoin was worth about $800, which was quite a lot even then. By the end of 2017, by December 2017, it had risen from $800 to $20,000 for a Bitcoin. And then on December 22nd, it went from 20,000 down to 14,000, lost a third of its value in a single day. And since then, over the course of 2018, has dropped down to $3,500. Now, this does not seem like yes, people have made a lot of money out of it, people who got in earlier. This does not seem like a stable, winning investment to me. But then, I don't know what I'm talking about with investing really. But the graph is like, so yeah, watch this space. Because just as many people that have made a lot of money inadvertently out of Bitcoin, there'll be a lot of people that have lost an awful lot more. And Ethereum has a similarly crazy trajectory in terms of the valuation going up and down. It's less crazy than Bitcoin because the numbers aren't as big, but it's like gone from $200 to $1,500 back down to 200 and all that sort of stuff. And yeah, if you were smart enough to have Bitcoin when it was at $20,000 and you sold it all, then brilliant, power to you. Otherwise, since then you've lost loads of money. So, before I move on to just the final bit, does anyone have any questions about anything that's come up so far? And I guess my question for you is, do you feel like you kind of understand how Bitcoin works now? Say no if you don't.
Kinda.
Kinda? Yeah?
I'm a guy who invested a lot into a version of,
Yeah.
and he lost it all, and he was like, he didn't know, I'll try and find him and send him a post.
Yeah.
He was in Japan or somewhere, and he went, how would this company sort of fraudulent, as in, sort of cancel, would they just cancel it, as in, want to go bankrupt him? Because he lost everything, and he went out there, he was in Japan, and he was...
You mean with regards to Ethereum Classic, what happened? Or
Like that, yeah.
I mean, I'm guessing your mate just lost his money, right?
Yeah, just lost everything.
Yeah.
He was,
I mean, I don't think these reversals of fraudulent transactions are not a common thing. I think this was just because it was so much money and it was such a big attack that, and clearly it was a controversial decision even with that to reverse that, because it spawned a whole new currency because of people disagreeing with it. But that seems to be the nature of the world of cryptocurrency. It's nuts.
How many cryptocurrencies are there out there?
I don't know, but a lot. There's a lot. Yeah, I mean, we almost made one here. You can make one pretty easily, and just start saying, Pedcoin is now worth, whatever. But you can start putting it out there and start giving people Pedcoin wallets and see what happens. Sorry, Jess.
How does, obviously we talk about it in the context of cryptocurrency, presumably blockchain has to work with other things.
Yeah, we're going to talk about that in a second. Yeah,
Okay.
yeah. Although not many. But yeah, we're going to talk about that in a second.
People
Yeah.
that, we're doing a startup for insurance using blockchain.
Yeah.
So is it just that their ledger is different things?
Yeah. So insurance is. We'll come on to it in a second. Yeah. Yeah.
So what's to stop a massive group of people deciding, let's just keep making extra forks of this so we can keep doubling our amount of coins?
Nothing. But you're doubling your coins to nothing because your fork doesn't have any value until it has value. So because it's not backed by anything. One of the key things about cryptocurrency in contrast to like pounds or dollars, even though good luck going to the Queen and saying I want my pound of gold, please. But they're still in theory they're backed by a government and they're backed by international trade and all that sort of thing. Regular currencies. The cryptocurrencies aren't backed so much by that yet. They don't have that history of that stability and whatnot that goes into exchange rates. They're incredibly volatile. It's like a tech bubble basically. They're just like in the zeros, people are going like, well, hang on a minute, we've got no idea what this is worth, but it could be worth a lot, so let's invest heavily in it just in case. And that's why you're seeing this crazy up and down sort of stuff. But there's nothing to stop that. There's also nothing to stop everyone getting together and deciding, well, between us we could control 100%, some malevolent organisation buying a shitload of PCs and saying, well, we're going to just control the whole thing. And then if that were to happen, over a long enough time, you could, one of these things could conceivably be like brought down in that way. There are alternatives to proof of work. So I talked about Bitcoin having a 10-minute thing per block. That's very long by cryptocurrency standards. Like Ethereum is something like 4 seconds it takes to generate an Ethereum block. And Ethereum are proposing moving away from proof of work. There are alternative systems to proof of work in terms of keeping your chain secure. Most notably one called proof of stake, which rather than, because another all of this, but another controversial thing about Bitcoin and proof of work as a system is how bad for the environment it is, because you've got all these, thousands and thousands of computers churning. They reckon that like each Bitcoin uses as much electricity as a single home in a year or something to generate. It's like huge amounts of electricity being used. Proof of stake, I'm not going to talk about proof of stake now, but I can send links around if anyone is interested in it. But that's a little bit different in that you just put up collateral. Effectively, you put up collateral to say, like, look, I'm invested in this, and if I defraud the system, you're going to take my money. So I'm obviously not going to, because I stand to lose. In the same, it's like
How much
No, because it's still distributed. It's still distributed amongst everyone. But it's like it's like me giving you a deposit to look after your phone or something. If I smash your phone, you're going to keep the deposit, or in your house or whatever. So it's that sort of principle, but applied to that. And what that means is you don't have that electricity cost or anything, but it still remains, in theory, secure. I can send a link around about proof of stake. But now on to what Jess was sort of getting at is, can we actually use any of this? Well, one of the sort of interesting things about blockchain is it's not a new technology. It feels new because cryptocurrency is new and, well, relatively new, but cryptocurrency's only got huge recently. But concepts underpinning blockchain were actually described way back in 1991. But it wasn't until 2008 and the Bitcoin white paper by the person or persons known as Satoshi Nakamoto, which could be Arnet. Bitcoin was created by someone claiming to be a Japanese developer called Satoshi Nakamoto, but their identity's never been revealed, and lots of people think it might actually just be a group of people that are protecting themselves by not revealing their identity. Something. But that was the first time that blockchain as a technology really found a home and really found a purpose and something that it was actually kind of good for. So, yeah, I guess what I'm trying to say is that this isn't, although interesting and useful and effective, is not something that's going to radically shake up the way we do everything, because it would have done already if it was going to. But that said, there are certainly, there are applications of it beyond cryptocurrency, and certainly in the industry, some of the industries we deal with. So Canada Life, for example, one of our clients, a huge feature of their product is this ledger of transactions. Now, it's a centralized thing, and that Canada Life would have no interest or need, I think, to have this decentralized public history of everyone's direct debit payments for their mortgage. So although ledger, the sort of, you think, light bulbs, we can do a ledger. You could, and it would be one of those things that would be probably a good selling point. It would be the sort of thing they could put on their website. Your money with us is backed by blockchain security or whatever. It wouldn't really mean much, but it's the sort of thing that someone could go for. They also do audit. It's useful as an audit trail thing as well. So if you're keeping like a log of everything that's happened on a system, this immutable property of blockchain is quite useful. I mean, if you're the one that controls the whole thing, it's not technically immutable because you could just rewrite the entire thing. But it adds a layer of security, and prevents sort of lay person tamperability. Insurance is another industry that's been exploring the potential applications of blockchain for some of its products. Again, I can ping a link around about that. I didn't go into that too much for this talk, apart from knowing that it's happening, and we obviously have insurance people as some of our clients. I don't know how mature the ideas that are being explored with regards to applying that, but it's all to do with transactions and new ways of selling, basically. But whatever the case, it's going to be getting easier to use this sort of technology because Amazon are about to bolster their already pretty colossally swelling array of services with not one but two new blockchain-related services. One called the Quantum Ledger Database, which sounds amazing, and then one called Amazon Managed Blockchain, which is a little more boring. The Managed Blockchain one is to make creating these distributed networks easier. The Quantum Ledger Database is, they sort of go out of their way to say this is not blockchain on their thing, but it sort of is in all but name. It's just an immutable database that they're going to be providing, basically, which will be for things like audit trail, activity logs, messaging. Like messaging platforms, probably a good use case for it as well. Something like WhatsApp. There's a benefit to knowing that messages you've received haven't been tampered with or removed or anything like that. You know, there's definite merit there. That's definitely a use case. But yeah, I applied for the preview of Quantum Ledger database, but they saw straight through me. I didn't get on it. So unfortunately, I couldn't show you any Quantum Ledger stuff today. But I imagine it'd be quite boring. It'll probably just look like a database. Yeah, that's it. Thank you. Are there any other questions? I don't think so.
So even though this is true, I heard that blockchain is responsible for why graphics cards are so expensive.
Yeah. Well, I think that is true. I think there was a huge spike in. That was right, isn't it? There was a huge spike in the prices of graphics cards because supply and demand, basically. They were just being bought by loads of people hoping to mine cryptocurrency in their bedroom. Because graphics cards in particular are extremely good at doing the sort of computations that are required to find those nonces.
Could Damien evolve the Kyan game further, create it as a currency, like
Kyan.
so points, and then we can have our own.
Yeah, you could. It's actually it's really not hard to actually kind of I was sort of half joking, but it's not hard to sort of create a cryptocurrency and create your own Kyan or Pedcoin or whatever. Just having gone through the process of doing it, not sure what merit there is in it.
So presumably, if you wanted to sort of do it at much lower value and lower effort, you could just use like a easier to solve hashing mechanism.
Yeah, and I think as a sort of academic piece, it's interesting. The complexity is in the networking aspect of it rather than the blockchain aspect itself. That's sort of self and in the optimization, I guess, as well. You know, if you're talking about something that's having like millions of blocks in it, the optimizations that are going to have to go into being able to actually inspect the whole history and validate things is probably where a lot of the work goes.
Do you think the distributed nature of it makes it more secure?
Well, yeah, that's the whole the whole underpinnings of its security are based on the fact that it's distributed and the fact that there's no one authority. Because if there was one authority, it kind of wouldn't mean shit really. It would just be a bank, and the only thing that would stop a bank from rewriting history or whatever is the fact that people would sort of kick off if it happened. You go, oh, hang on a minute, I had £100 in my account yesterday, and now you're saying I've only got 50. But there's nothing to stop a bank from doing that and just going. Yeah, but it does mean this, the nature of the security and the nature of the fact that the security is linked to how long your chain is. It does mean that as soon as a new block appears, you don't really know whether to trust those transactions in it at that point, and not even at that point, but only once you've got like 10 blocks down the road can you look 10 blocks hence and go, actually, yeah, everything in there is probably legit now. So it's a slow process, trading in Bitcoin, which again is why it feels like it's accepted by very few retailers in America, like top retailers in America. It feels like its home is largely in currency traders and in people looking to kill their spouse or buy a shitload of drugs or whatever without being traced. Thanks.
ADLTD, whatever he is.
ADLTD.
Amazon Deep Learning Teledildonics.